Well, thank you very much, Peter. I feel greatly honored. I also feel rather humbled by the words you just spoke. All I did was having a lot of fun while looking at roots, really. And I want to share that fun with you. And I hope you will also agree that working on roots is actually a lot of fun, and you can make fantastic new discoveries. And I've been able to contribute to that. Our paths have crossed in many ways, I think. I may have reviewed your papers and you didn't know that. I may have rejected some of your papers, and some of you always come up to me at conferences and they look at your bed and say, "Oh, you were the one who rejected my paper." Not true at all. I have just happened to be editor-in-chief of a journal that receives a lot of papers, and 80% of those get rejected. And if yours was one of them, don't necessarily blame me for that. Anyhow, enough of that. I want to talk about these fantastic roots. We call them cluster roots. And although I don't want to go back in history too far for too long, there are a few papers I would like to list here today. It was actually a German in the end of the 19th century who discovered these funny roots in Australian plants. They were actually Banksias growing in the botanical garden in Leipzig. And he described them in detail, and then they were forgotten until somebody in Victoria, in Melbourne, Helen Purnell, actually started looking at them again. And she actually made a whole inventory of lots of Australian species in the family of the Proteaceae, and discovered they all made these rather funny roots, as you can see over here. And because they were first discovered in the family of the Proteaceae, they were then given the name proteoid roots. Well, after that, Bill Gardner came along, and that's actually rather personal for me, because Bill was mad as a cut snake, and he hasn't actually changed one little bit. But he did fantastic work for his PhD at Melbourne University while I was a postdoc there. And he was actually working on lupins, and lupins also make these proteoid roots. And here are some photos from his early work, and he basically showed they dissolve calcium phosphates. And he also worked out how they actually did that. And they also dissolve manganese oxide, and I'll come back to that idea of manganese later during my talk. And this is one of our own photos showing that even years later, Michel Watt followed that up, for example, even years later, those proteoid roots in lupins received a lot of attention. But we then realized that they weren't clearly restricted to the Proteaceae. They were found in lupins, for example, and in fact they are found in quite a few Fabaceae. And only a few weeks ago I dug up a species that I suspected might make them, and indeed it also produces these wonderful proteoid roots. And so it was actually time it was decided to give them a different name. And so instead of proteoid roots, we now usually refer to them as cluster roots. And they are typical in a lot of Proteaceae, and they are also typical in species that form a symbiotic association with Frankia. And I suspect that all species that have that symbiotic association with Frankia actually make these cluster roots. Now, if you look at Banksias, for example, that's a genus that is mainly restricted to southwestern Australia, but they also have a handful in eastern Australia, I must admit, but they make these wonderful compound cluster roots. But if you go to other species, then they look a little bit different. But you don't have to stick to cluster roots. You can also go a little bit further and go to these roots that we find in Cyperaceae, for example. And Cyperaceae, sedges, that's a cosmopolitan family. You can find them all over the world. And a lot of these, they actually make these sorts of roots. Morphologically, they are very, very different, but functionally, as I will show in a minute, they are actually very similar to the cluster roots in Proteaceae and in Fabaceae. And then in Restionaceae, the southern Rushes as they are often called, because they are a southern hemisphere family, we have these capilloid roots. And I'll show you in a slide in a minute that they do exactly the same. And then, you must have seen those, for example. These are scent-binding roots. And they may play a role in water relations, but they also clearly play a role when it comes to nutrient acquisition, and they do exactly the same what these cluster roots do. Now in Brazil, in the Campos Rupestres, we have done some work on a cactus, for example. And this happens to be a non-mycorrhizal cactus, and what this cactus does is actually exactly the same as what Proteaceae do. And then, most excitingly, we have some species that grow on the rocks, literally on the rocks. And I wondered where these species actually got their nutrients from. And the first suggestion was they get it out of the litter. That was my suggestion. Now that was a pretty daft idea really, because the litter that you find over there is actually the litter they have produced themselves. And there's no such thing as a perpetuum mobile, so these plants did not get the nutrients out of the litter. And then one of the students said, oh, they probably get it out of the rocks. And I thought, well, that's a pretty daft idea. But she was actually spot on. What these plants do is they grow in the roots, they drill little holes, chemical holes, in the roots, and they look like this. And we are now discovering that they actually behave exactly the same as the roots that we have studied in detail. And here we use the facility, the synchrotron facility in Brazil, in Campinas, and we can really see where the phosphorus is, and where, that's labeled over here, where the phosphorus is, and also where the zinc and the calcium and the iron and the manganese actually is. Now this is all work in progress, but we are trying to use that synchrotron facility to learn a little bit more about what these fascinating roots are actually doing. And then sometimes roots don't have any specific morphology at all, and yet they can still release massive amounts of carboxylates, because that's what cluster roots are all about, releasing massive amounts of carboxylates. And what you see here is that there's a lot of variation in this species over here, chickpea. There's a lot of variation. Some release very few carboxylates, and some release massive amount of carboxylates, and that correlates neatly with the amount of phosphorus that these plants actually manage to take from this particular substrate. So lots of different morphologies, but they have one thing in common, and that these structures are rather ephemeral. In this example, which from a paper that we published quite a few years ago, these structures are only about 21 days. And if you only live for 21 days, you're really in a hurry. That basically means that you work fast, and if you work fast, you respire fast, and that is exactly what you see over there. Respiration rates are very rapid in the first few days, and then it slows down. And what is the carbon used for then? Then they start making carboxylates, mainly citrate, also a bit of malate, and they pump that into the rhizosphere. So a lot of the carbon is actually used to pump out these substrates. Now, Michel Watt already discovered that in lupins. We decided to do that also for these Proteaceae, and indeed they also release their carboxylates in an exudative burst. And so do the Cyperaceae, but these are even more in a hurry, because they only last for about 10 days. And during these 10 days, you can see they release massive amounts of citrate in an exudative burst. And then, rather new, these capilloid roots of the Restionacea, Michael Shane a few years ago also measured the exudate release there, and again they release citrate and to some extent malate also in an exudative burst. Now I don't want to say that all these plants that release these exudates, they always release them in an exudative burst. That's what I thought for a while, but that's not what is the case at all. If you look at these compound cluster roots of these two species of Banksia, for example, they do release carboxylates too, but here what they do is they release that at a steady rate during their entire development over here. So this is the release from non-cluster roots, this is the release from early states, immature, mature states, and the exudation rate is actually pretty steady. So that's a different strategy, and it probably allows these plants to grow on really severely nutrient impoverished soils. That strategy may work better there, because that is where we do indeed find these particular species. So what do they do? Well, they produce massive amounts of carboxylates. They release that via carboxylate channel, and so the carboxylates then enter in the rhizosphere. And there the carboxylates, negatively charged organic ions, they take the place of phosphate and they push the phosphate in solution. If that's organic phosphate, it will need to be hydrolyzed. If it's inorganic phosphate, it can be taken up straight away. So there's nothing specific about the phosphate transporters of these plants. They are pretty similar to what we know of phosphate transporters in Arabidopsis or rice or what have you. What is really special about them is the release of massive amounts of carboxylates that mobilize the phosphate that other plants can't get hold of. So these plants, when it comes to soils that are severely phosphorus impoverished, are actually superior to what mycorrhizas can do. That is what I'm claiming, and that's what I want to convince you about. Now, I could have known that many, many years ago, but sometimes you have to go back to the old literature and read it with new eyes, and then all of a sudden it falls into place. So this work was done actually at the same university as I'm based right now, and Roger Parfitt actually used goethite, being the mineral that is in soil and tightly binds phosphate. He actually used goethite to then work out how much phosphate will actually be in solution over here, depending on the amount of phosphate that we add to the pots in which the goethite was present. And you can really see you can give a lot of phosphate to that goethite, and there's nothing in solution. It all gets absorbed onto this mineral in soil, a real mineral. You can do exactly the same with aluminium hydroxide, but it's not a mineral that occurs in soil. This one does occur in soil. And so, if you add more and more and more, then finally the concentration in the soil increases, and he went to about 20-25 micromolar over there. Now, he was a soil scientist, but he was also interested in plants, of course, because soils are only interesting because of the plants that actually grow in them, and he was blatantly aware of that, and he basically found out that there's no phosphorus available for ryegrass until about 40% of all the sites of goethite that can bind phosphate are saturated with phosphate, with phosphate, yes. And the maximum amount of phosphate that is available occurs around 2 micromolar, and that's when about 75% of all your goethite sites are covered by phosphates. And the mycorrhizas he then discovered, the mycorrhizas are only effective in the range of 0.5 to 2 micromolar phosphate in solution, and that's there. So above that, the ryegrass can do the job all by itself. It doesn't need those mycorrhizal fungi. Below that, neither the roots can get it by themselves, nor the mycorrhizas can actually get it. And that is where these cluster roots, these proteoid roots, and all these roots that have those specialized structures actually come into action. So when phosphorus is either very nutrient poor in soils, or when it is strongly bound to soil, that's when you need the carboxylates, and that's where the mycorrhizas are pretty useless. So are they really less effective in phosphorus uptake when soils are very infertile? Well, Paul Riddell years ago did a wonderful experiment, and I knew about it for a very long time, but he never actually published that. And then when in 2015 we actually published this chapter in a book, I said to Paul, we must get this out in a literature because it's actually a magnificent experiment. Because what Paul actually did is he worked with Proteaceae, my favorite family. But in his part of the world there is also a Proteaceae that does not make cluster roots but makes mycorrhizas. And here he had the opportunity to actually compare the performance of plants with cluster roots, being non-mycorrhizal, and plants that are mycorrhizal but without making cluster roots. And what you can really see is this is where the plants that produce cluster roots achieve their maximum weight as a function of the phosphorus concentration in soil over here, and you've got to double the phosphate concentration, and that's when the mycorrhizal plants actually achieve their maximum growth. So this clearly demonstrates that indeed those mycorrhizal plants, they are fine when soils are a little bit poor, but when soils are very poor and phosphorus is all locked up in the soil, that's when mycorrhizals can't do the trick. That's when you need these carboxylate releasing structures. For example, proteoid roots, but dorsiform roots or sand-binding roots are just as good. And it's not just about soils being poor like they are to a large extent in Australia and also in Brazil. It's also about soils that are strongly phosphate-absorbing, like we have in southeast China, for example, like we have in large places of Brazil. And you would have that in soils in Israel too, where the soils can be very calcareous. That's when the phosphate is all locked up, and that's when this strategy is actually better than a mycorrhizal strategy. So, this is how it all works. The carboxylates are released, they release the phosphate, but in that process they also release, and we knew that already from Bill Gardner's work, because he had those agar plates where he showed that manganese was dissolved, they also dissolve manganese. And so these plants that release massive amounts of carboxylates, they always end up with large amounts of manganese. And I thought, perhaps you can use that manganese concentration as a proxy for what these plants are doing below ground. Digging around for roots is a lot of work. Measuring exudates in the soil is a nightmare. You can do that in the glasshouse, that's fine, but doing that in the field, just forget about it. It just doesn't work. It's just too complicated. So if you could use that manganese concentration as a proxy for what these plants are doing below ground, you would be in business. Now in Western Australia, we have a dune system just north of Perth over there, and that dune system is characterized by very young soils, very young sands, only a few days old, a few years old perhaps, and also sands that are more than 2 million years old. So we've got a chronosequence over there. And the vegetation along that chronosequence changes because the soil properties change. What typically happens with all chronosequences is that they start with very low nitrogen concentration. Beach sand doesn't contain any nitrogen, so the nitrogen-fixing organism will have to bring that in, which is what they do. So it goes up and then it goes down again, because for nitrogen fixation you need phosphorus. And as you can see over here, the phosphorus concentration is very high to begin with. So beach sands is one of our richest soils in Western Australia. And then the phosphorus concentration goes down, and because of the decline in phosphorus concentration, the nitrogen fixation also slows down. So we end up with very, very nutrient-poor soils. But they are particularly low in phosphorus. Nitrogen is also very low, but that's not the key limiting factor. Okay, so we've got a wonderful chronosequence, so we can look at all sorts of strategies that actually change along that chronosequence. But what's really very interesting is this. Total soil phosphorus declines, and if you look at the species richness, we can actually see that the poorer the soils, the richer the flora. That's typical for that system. That's actually typical for the whole of the southwest of Australia, and in fact, wherever you go in the world, you find the greatest biodiversity where soils are the most phosphorus impoverished. But that red line is really interesting because those are my proteacea. And you can really see those proteacea barely occur when soils are a little bit richer, not rich by European standards, but rich in our system over there. And then they really increase, so those proteacea, they really pick up the poorest of the poorest soils. That's where they do well. And in fact, we've got other non-mycorrhizal plants as well. They do exactly the same. And what we can then see, when we look at the mature leaf manganese concentration, we can really see that that concentration really depends on the strategy the plants are using to get phosphorus. If you look at the typical non-mycorrhizal strategies, these plants have the highest manganese concentrations. And these other strategies, well, those manganese concentrations are considerably lower. And if you look at it as a function of time, so these are the 2 million old year dunes and these are only a few hundred years old, we can really see that the phosphorus concentration actually increases. It mainly increases in the non-mycorrhizal plants, but even in some of the mycorrhizal plants, it actually tends to increase. Why does it increase there? Have they switched strategies? No. They've actually discovered that it is actually very nice to grow next to a neighbor that can do all the hard work for you. Then you don't need to bother about doing all the hard work yourself. You can just steal a little bit of phosphorus. Well, it's stealing. Well, it was there anyway. So they basically take up the phosphorus that the neighbors have mobilized for them. So even in those mycorrhizal plants, the manganese concentration can go up a little bit. So it's a fantastic way to make an inventory of the whole ecosystem and get an idea what these plants are doing below ground without even doing any shovelomics. This is as good as shovelomics, but you need to first establish that correlation actually works, and that's where your glasshouse work comes in. That worked in southwestern Australia. Well, it also works in Brazil, where again we find all these non-mycorrhizal cacti, for example, with high manganese concentration. And if you look at all the arbuscular mycorrhizal plants and the non-mycorrhizal plants all have higher manganese concentration. So it works as a proxy. Proxy in ecology. Is it useful in agriculture? Can you use it in breeding? And the answer is yes. Jane Pang did some wonderful work where she looked at more than 200 accessions of chickpea, then narrowed it down, because if you want to measure leaf manganese and you want to measure root carboxylates, that is so much work you can't do that with more than 200 species. So she narrowed it down to 100, and what we can see over here is the manganese concentration, and here we see the root carboxylates. Now let me magnify that a little bit. So you see the manganese concentration over here, the carboxylate concentration over there. In this particular case, in chickpea, most of those carboxylates are not citrate or malate, they're actually malonate. But a beautiful correlation. So rather than go through the trouble of measuring malonate or carboxylates in the rhizosphere, all you need to do is measure the manganese concentration, and you know what these plants are actually doing below ground. A wonderful tool in ecology, but equally in plant breeding. So this would be typically a genotype that does not release a lot of malonate. That would be typically a genotype that you would want in an environment that may be a little bit phosphorus impoverished, but not too severely. That's where the mycorrhizals can do the job, and they can do that cheaper than the carboxylate releasing strategy can do. But when phosphorus is strongly resorbed over it, or it's simply not there, then that is the genotype that you would want to breed for in that particular environment. So we've got a breeding tool now, and that can really help us develop the right genotype for the right environment. So some people say I'm obsessed about cluster roots, but people say so much and you shouldn't really believe what everybody is saying. So the story here really is that I'm not obsessed about cluster roots. I'm obsessed about a whole range of roots, really, because these dorsiform roots do exactly the same, or the capillaroid roots, or the sand-binding roots, or the velocioid roots. You can have a whole range of root species of root structures that do exactly the same as what those original proteoid roots actually do. That's fascinating. And sometimes you don't even see a structure, and still those plants may be releasing massive amounts of carboxylates. And we don't need to measure all those carboxylates anymore. Well, you may want to ground truth it at some stage, but I would begin with leaf manganese concentration, because they give you a pretty good indicator what is likely happening below ground. And if you find a very high or very low concentration, then you can start looking for the carboxylates in a glasshouse study. Don't do it in the field, you're wasting your time. Now, lots of proteaceae make cluster roots. The ones in southwestern Australia do that, the ones in South America do that too. But the soils in South America are very different from the soils in the sandy soils that I just talked about, that are severely phosphorus impoverished. In Chile, for example, we are dealing with young volcanic soils. They are loaded with phosphorus. So, and I knew there were some proteaceae there, so I wondered, will they actually make cluster roots? So when I started getting involved in teaching a postgraduate course there a few years ago, I wanted to know, do they actually make cluster roots? And the answer is, yes, all of them make cluster roots. But then the question is, why do they do that? And the answer is, well, that phosphorus is actually very hard to get, because the pH is very low, those soils are loaded with aluminium and iron oxides and hydroxides, so it may be there, but mycorrhizas or other non-mycorrhizal plants can't actually get that. But for these cluster roots, it's no problem at all. But these cluster roots actually are designed in a different way from the ones I was so familiar with in southwestern Australia. So these make a massive amount of cluster roots, and I'll give you the figure in a minute, but they are big ones, lots of them, and they release carboxylates at what I thought was a rapid rate, but everything is relative. If you go to South America, these plants don't actually make a lot of these cluster roots, a lot less cluster roots, but these release carboxylates at a much faster rate, and that all makes sense, which I want to illustrate over here. Here there's plenty of phosphorus available. There's plenty of phosphorus, but it's poorly available. So you keep pumping and pumping and pumping those carboxylates out, and you will get more and more and more in return. You don't need a lot of these cluster roots, but they need to work very, very hard, and then you get your phosphate in return. Here it makes no sense to pump a lot more of these carboxylates, because in those sandy soils there is simply very little of that phosphate, and a little bit of carboxylates will actually do the trick. So yes, these exudation rates are relatively fast compared to other species, but they are nothing compared to what we find over here. Here they last for about 3 weeks, because after that everything has been depleted. Here they last for about 4 weeks, because there's plenty of phosphorus that you can actually extract from those young volcanic soils if you have the right strategy. Life is all about trade-offs. That was a nice trade-off where you can decide, shall I make a lot of these clusters, or shall I make them work very hard? And different decisions were made depending on the soil. It's really about plant-soil interactions. But there are more trade-offs when it comes to these cluster roots. So this is a nice example of trade-offs. You can have a great education, but that may mean that you will end up with a boatload of debt. And you can either want one or the other, but you can't have both. So what is the trade-off that plays a role here? Well, as I pointed out before, these roots live for about 3 weeks, and they're really designed to pump out large amount of carboxylates, and they haven't really thought of defending themselves against pathogens all that well, we thought. So that might be the trade-off. You're good at one thing, getting the phosphorus, but you're not so good at defending yourselves. That might be the problem over here. And so we did an experiment, and you can read all that. You can also look at the data over here, but one picture is worth more than 1,000 words, so I just give you 2,000 words in those two pictures over there. What do those pictures show? Well, this is a Banksia, one of these Proteaceae species that do so well on those very nutrient-poor soils, and that grows in soil that has been sterilized. We don't like all these pathogens, so we sterilize our soil, and this plant grows well over there. That soil was a natural soil. The only difference between that soil over there and the natural soil is that we had it pasteurized. Now, if you don't sterilize the soil, then you end up with this pathetic looking little plant. So this plant clearly is very sensitive to nasty pathogens that have not been killed by sterilizing the soil first. And they're all oomycetes. Pythium is one of them, and there are also a number of native Phytophthora species. So these Proteaceae are particularly sensitive to these pathogens. And I think we may understand why they are so sensitive. What you show over here, what you see over here is cross-sections of not just the cluster roots, but also other roots. Doesn't matter which part of the root you actually look at. What you clearly show over here is a wonderful endodermis, but what you also see is that none of these plants None of the Proteaceae that we looked at ever make an exodermis. Now, this exodermis would be a great barrier to keep your nasty pathogens out. These plants don't make that exodermis, and so the pathogens can actually walk in and hammer that plant. And so if you now do an experiment where you grow one of these Proteaceae that's very good at getting the phosphorus, together with one that's not very good at getting the phosphorus, and you do that experiment in a sort of complicated way where you have the pathogens present over here, and you also have the mycorrhizal fungi present over there, then let's begin with the situation minus Phytophthora. Then these mycorrhizal plants, they actually are not affected, and that's actually an average of 3 different species. These mycorrhizal plants are not at all affected by the degree of colonization by ectomycorrhizal fungi. Now, what that actually tells me is that these fungi do nothing in terms of delivering phosphate to these plants, because then you would expect a much better growth over here than over there. That's not what we find. But if we do repeat that experiment, but now have the Phytophthora present because you don't sterilize those soils, what you then see is these plants do very poorly there, and that is because the other plant that can mobilize the phosphorus does very well, but they do very well over here because those plants that get hammered by the Phytophthora don't do very well. So let me summarize that in this little cartoon over here. Let me begin with the situation with the pathogens removed because of sterilization. We have our cluster-rooted plant over here that mobilizes the phosphorus, and it does that all for its own good, of course, but the neighbors actually pinch a little bit of that phosphate, but there is some competition going on, but there's also massive facilitation going on. So that is without having any Phytophthora, without any pathogens present. But now let's go to the real world. What we see then is that this plant gets really hammered by the pathogens. It still mobilizes a lot of phosphorus, and this plant really loves that because now it can actually steal more of that phosphorus because it's not all being used by this plant whose growth has been slowed down. So in that very nutrient poor system, which is very biodiverse, we now are beginning to understand why we have that tremendous biodiversity, at least in the Southwest Australian biodiversity hotspot. It's a combination of facilitation being more important than competition in that very nutrient poor system. These cluster roots are very important, but so would dorsiform roots and sand-binding roots be, all non-mycorrhizal structures. These plants may have mycorrhizas, but these mycorrhizas are really very useless when it comes to taking up phosphate, but they are very important in boosting the defense against pathogens. So the mycorrhizas do play an important role, but not for phosphorus uptake, but for boosting the defense. And then those pathogens, they secure a sort of equilibrium between these plants that are very good at getting the phosphorus, but are not very well defended, and these plants that are not very good at getting the phosphorus, but are much better defended. It's all a matter of trade-off. And this plant has made a different decision from that plant over there. And together they can coexist, and that's why we have that tremendous biodiversity. So, minus pathogens, and here plus pathogens over there. Now, the situation in Fabaceae is actually rather similar to what we find in Proteaceae. A lot of Fabaceae, and Michel Watt's work on lupin indicated that, our work on chickpea indicated that, a lot of Fabaceae also release massive amounts of carboxylates. Sometimes with a specialized structure like sand-binding roots or cluster roots, sometimes without a specialized structure. But what this slide clearly shows is, again, a wonderful endodermis, but no exodermis. So the staining, and that is typical for all Fabaceae that have been looked at, Fabaceae do not make an exodermis. So our current thinking is, and I'll leave that with you without wanting to convince you that this is how it works, but our thinking is that both Proteaceae and Fabaceae, they are known, I might have wanted to put an N there, but I left that out, are known to release large amounts of carboxylates. And it is possible that the absence of the superized exodermis may well be essential to allow these plants to release those massive amounts of carboxylates. That's our current way of thinking. But that lack of an exodermis also makes these plants very vulnerable to pathogens. Now, of course, you could decide to have no exodermis and release massive amounts of exudates, but be mycorrhizal at the same time. And some plants do indeed exactly that, some legumes, for example. And it might be that those mycorrhizals are pretty useless in getting extra phosphate in that environment, but they may actually be very important in boosting the defense of these plants. So perhaps that's why some plants are both mycorrhizal and release a massive amount of carboxylates. But clearly there is a trade-off. But when you go to Cyperaceae and also Velociaceae, they definitely do have an exodermis. And that makes me wonder whether perhaps these use their root hairs to release their carboxylates. At the moment, we only know that massive amounts of carboxylates arrive in the rhizosphere, but we don't know whether they have been released by the exodermis per se or by the root hairs emerging from the exodermis. I think that still needs to be determined. But it is just possible that the lack of an exodermis is very important to release massive amounts of carboxylates in Proteaceae and in Fabaceae. Now, I may have given the impression, because I got the award after all, that I did all this work, but I hate to disappoint you, because there's a cast of thousands behind every slide that I actually showed you this afternoon. All I did is pull it together and present the talk and convince you that work on root research is nowhere near over. There is still a lot that can be done. Thank you.
Would you be willing to answer a few questions from the audience?
Yeah, I'm happy to.
Pressing questions.